Welcome to the final talk of the day. So our final speaker is Nishad, PhD student from Nishad Group at Harvard, and he'll tell us about digital quantum simulation error correction with Rydberg atom arrays.
Thanks, Yincha, and thanks to the organizers for inviting me to speak today. So I'm very excited to tell you guys about some recent work that we've been doing in terms of digital simulation and error correction with Rydberg atom arrays. So it's going to be a bit of a change from some of the prior talks. This one's going to be much more focused kind of on like a experimental path forward in terms of quantum simulation. So, one of my main motivations for working on quantum computing is actually using quantum computers as a powerful tool for learning and understanding things about quantum antibody physics. And, over the last 2 decades, there's been a lot of very exciting experimental work with analog quantum simulators that have made a lot of progress understanding and characterizing things like topological phases of matter in programmable quantum simulators, and also, in fact, some kind of discoveries of new surprising quantum dynamics phenomena using these, analog devices. And while these devices are still noisy, the thing that really gives them a lot of power is the fact that you're really natively working with the interactions that the system naturally engineers. So in that sense, there isn't too much overhead associated with these types of problems. Now, in the long run, one of the things that we would really like to be able to target are realistic simulations of real molecules and materials, and we really move towards taking these devices and using them as tools for doing science. And, these models are much more complex, and as such, to really start to target them, we're going to need to consider an approach that really allows for full programmability. And so that's kind of really where some of the digital ideas that we're going to be discussing today on the hardware side are going to start to become very important. And while I'll often kind of focus on molecules and materials in the talk today, I also just want to take a step back and take a moment to highlight how, really simulating quantum antibody physics is really a central aspect of computational science today. So, here, for example, as a heuristic, you can look at the DOE breakdown of what the supercomputer is used for. And you see almost 3/4 of the fields that dominate usage really at their core are bottlenecked by simulation of some strongly correlated many-body physics problem. So, quantum computing potentially has a way of a potential to enhance a very wide swath of computational science. So, given all the potential applications, it's really important to now also try and ask, how expensive would these simulations be? The really important, really impactful ones, even if we have really good quantum hardware. And yeah, Lynn.
Do we know that they're strongly correlated?
No, we don't. Yeah. So, this is why I say potential to enhance a lot of these applications. Currently, we, of course, put most of our effort into things that we can do well. So yeah, these are all using classical methods. Okay, good. Yeah. But, even then, among the big subspace of problems that people study, there are a small fraction that we know involve large amounts of strong correlation. And so we can start to ask, how expensive would it be to really start to try and study some of these systems with their quantum computers? And, luckily, recently, the team at Microsoft did some pretty detailed resource estimates, taking kind of existing state-of-the-art algorithms and applying them, kind of seeing how expensive they would be to apply to these types of problems. And, some of the kind of early estimates are a little pessimistic or a little concerning. So, if you take, for example, the problem of studying the active space Hamiltonian of some ruthenium catalyst, you find that, even on futuristic quantum hardware, it might take on the order of months to do a single electronic structure calculation, a single energy calculation using this type of system. So, this is both a concern, but also an opportunity for understanding where should we focus our efforts in order to try and really make these kind of push towards realizing these applications. So kind of along those lines, there's really three sources of overhead that go into solving these types of problems on a quantum computer. One of them is the mapping of the application problem to quantum hardware. The next one is actually the quantum algorithm itself. And the third one is also the overhead that comes from quantum error correction. So, kind of as like a high level picture for some of the stuff I'm doing today, what we're really trying to do at a high level is figure out, can we co-design various aspects of the quantum computing approach, the algorithms, the architectures, and the applications, in order to really try and bring these resource costs down, to really try and make impactful, really make impact in computational science as soon as possible.
Trying to make sure I read the figure correctly.
Yes.
It says that for quantum chemistry, I need like a century and 10 million qubits to solve some problems.
Yeah. So each of these dots here is kind of like a different hypothetical architecture, a different hypothetical hardware, with some physical error rate and some clock speed. And so depending on the physical error rate, it really affects how much overhead comes from quantum error correction. And then depending on the clock speed, it tells you, kind of rescales the axis here. Then the vertical axis here, a lot of this overhead comes from actually the error correcting code itself. So, you oftentimes have to use on the order of like 1,000 physical qubits to encode one logical qubit to really pull off a high fidelity simulation. Yeah, so these are kind of physical qubits on the axis here. Yeah, these numbers are big.
Yeah. You think these are pessimistic?
So I think we're actively working on developing techniques to improve these numbers, but they're not like order of magnitude. I think they are like accurate. Yeah, I don't think they're too pessimistic. Yeah, I think order of magnitude, given the current state of the art, yeah, they're in the right ballpark. Yeah, so I think it really is like a push to motivate us to try and cut things down wherever we can. Cool. So yeah, so okay, so that's kind of like that's kind of thinking in the future. Let's also kind of take a moment to think about the state of quantum computing today. So a lot of progress has gone into developing quantum hardware over the last 10, 20 years. And today we can readily implement complex quantum simulations and quantum circuits on roughly 100 qubits with error rates that are on the order of 99.5%. And people have really been using these devices to kind of pursue this like NISQ era of quantum simulation, where we can now start to play with simple quantum simulation algorithms and small systems and noisy systems and kind of get a sense of what does this landscape look like. However, as many of us know very well, if we really wanted to solve the most interesting problems, it's going to be really important that we can make these error rates orders of magnitude smaller. So, roughly like error rates of 10 to the minus 10 are probably important to start trying and pulling off some of these like quantum chemistry style applications. And the only way we know how to do this is really quantum error correction. So, remarkably over the last 2-3 years, there's really been giant strides in terms of experimental progress, in terms of being able to start demonstrating some of the key components of the quantum error correction, the key building blocks of quantum error correction. And there's been some really nice recent work in terms of how to preserve a quantum memory that gets better and better as you increase the code distance, coming out of the Google team. So there are kind of these two different eras that we're living in parallel, the NISQ era and the early fault-tolerant era. And today, what I'm going to really focus on is kind of talking a little bit about our efforts in quantum simulation in both of these domains. So on the one side, we're going to talk about some new ideas for pursuing digital programmable quantum simulations with physical qubits. And on the other side, I'm also going to talk a little bit about some of our recent works exploring early forms of error detected quantum circuits. Yeah.
Early fault tolerant.
So actually, I think in the example that I give, it'll be very clear why it's early fault tolerant. There, we're just using error detection. So it's clearly not scalable. We're really using tricks like post-selection, error detection, like soft margin decoding in the early fault-tolerant era to kind of push the numbers as good as we can. Yeah. So I would say, for example, an error rate like 10 to the minus 6 is something that's like probably achievable in the early fault tolerant era. Whereas these error rates of like 10 to the minus 10 are maybe slightly farther down the road. It's not a rigorous definition, but kind of, yeah. That's kind of my sense of the landscape.
Error detection, but not correction.
We're using tricks that are not asymptotically scalable. Yeah. So things that come with like potentially exponential overheads here. Yeah. And, I think kind of like a good motivation for this type of work is also, while we're doing it, try to really extract the lessons, what lessons can we learn now that could potentially help us motivate and design, future error-corrected quantum simulations and quantum algorithms. Okay, so, that's kind of going to be the rough structure of the talk today. I'll give some background on the platform and then dive into some ideas on the quantum simulation side and on the error correction side. So the platform that we're going to be focusing on is known as Rydberg the reconfigurable Rydberg atom array. And in this platform, we actually use neutral atoms that we trap in optical tweezers. And really, by using the tweezers, we can control the position of these atoms with quite a bit of like parallel control. And really, the parallel control of these atoms with tweezers is going to be like a key component of the architecture. We're going to encode our qubits in the hyperfine degree of freedom. And in particular, these qubits are very long-lived. So we can use this time to actually do things like move the atoms around. And when we want to generate interactions, we're going to drive to this highly excited Rydberg state. And it's going to be the Rydberg interactions that we use to really generate something like a two-qubit gate. And this architecture is really nice for a few reasons, in particular, things like non-local connectivity and parallel control. So without getting into it in too much detail, just to get a sense of what goes into the architecture. In the lab, my experimentalist colleagues have a computer that they use to control a spatial light modulator. The spatial light modulator takes a laser and splits it up into many parallel beams. And these parallel beams go into the vacuum chamber and form one of the sets of traps. You can use these traps to essentially grab rubidium atoms in the vacuum chamber. And you can use this to actually get, over 1,000 rubidium atoms just trapped in these optical tweezers very reliably. However, you'll see here, this is kind of like a pattern with kind of random filling. So now if you wanted to be able to manipulate the position of these atoms, they introduce one extra tool, which is this cross-Acousto optical deflector. And this essentially introduces a second set of traps into the platform. And now by kind of using these two traps, you can actually move atoms around and reconfigure the array. And one of kind of the first things that really made this a very powerful tool was that you could use this to remove defects, to create very large defect-free arrays. And you can also create more complex geometries. So my experimental friends love to have made a little video of an atomic Mario going around. And yeah, just to get a sense of, we can really make arbitrary patterns. Now, okay, so now what about the interactions? So just to give kind of a quick high level there, when the atom is in the hyperfine state, it's very small and well isolated from the environment. Then when we drive it to the Rydberg state, this electronic state is nearly unbound. So the atom actually becomes physically very large. And so if we now have two atoms that are near each other, and we simultaneously try to drive both of them to the Rydberg state, they actually have strong van der Waals interactions between the two Rydberg states. And the strong van der Waals interaction actually generates a very strong nonlinearity that we can use to create entanglement. So this entanglement, for example, and this is known as the Rydberg blockade effect. So for example, if you just take two atoms that are in the ground state and you simultaneously drive them on resonance, then the doubly excited state is so far off resonance because of the van der Waals interaction that you only generate oscillations between the ground state and the two singly occupied states. And essentially you can use this to create, for example, a Bell state. The Rydberg state that we're driving to is a state. Yeah. There are 50 to 70, so actually just one. Depending on the setting, they'll tune the principal quantum number of the state that they drive to because they have different like decoherence properties. Yeah. It's actually like we use a different n in sometimes the digital setting and the analog setting. Yeah, great question. Yeah. Oh yeah. So great. Yeah. So this platform can be used to do analog simulation. So in the analog setting, you kind of take the atoms, position them, and then just drive globally with time-dependent Rydberg beams. And you can use this to study all kinds of things like phase transitions. You can study early forms of combinatorial optimization algorithms, and you can definitely access interesting non-equilibrium dynamics. Now, on the digital side, ultimately, we want to start implementing quantum circuits. And these quantum circuits allow us to do universal quantum computation. So this is in principle a much broader setting of circuits that we can implement and therefore have many more degrees of freedom. However, we can still control these degrees of freedom efficiently classically. So in particular, the way that we program circuits is by using position to set the connectivity. So as I was describing earlier, atoms that are close to each other interact. And because the van der Waals interaction is 1 over r⁶, atoms that are far away from each other don't interact. And therefore, if you just position the atoms near the ones that you want to interact at a time, you can apply global laser pulses in order to realize 2-qubit gates or even 3-qubit or 4-qubit gates potentially as well. Then you can move the atoms around coherently and use that to get a different configuration where you then again reapply the global laser pulse. And so, what they've started doing in the lab is really kind of chaining these operations together to start realizing complex quantum circuits.
These shuttling times needed.
So the shuttling times are, I think, on the order of like 100 microseconds. And the coherence time is on the order of seconds. So you can get quite a few shuttles in before the qubit coheres. Yeah.
Have you measured times compared to that?
They're also on the same order of magnitude.
Oh, wow.
Yeah. So like the imaging time is also around same order of magnitude. Yeah.
So essentially about 10 or 20 shuttles until the qubit totally decoherent.
Roughly, yeah. You can tune how fast you shuffle to also like, in principle, make it higher fidelity. Yeah.
Reason why we cannot do it, but like make it longer or more shuttles.
So ultimately, then we would start to become limited by the 2-qubit gate fidelity. So like, we want to move the atoms around, but then we also want to apply interactions. And these interactions are still limited by this 99.5% fidelity. And that's really like the dominant source of error in, I think, in our platform at the very least. Great question. Okay, so that's like a little bit of an overview of the platform, just to get a sense of like the tools that we're playing with. And next, I'm going to talk a little bit about, kind of an approach that we've been pursuing for actually trying to realize interesting near-term models inspired by chemistry and material science. In particular, I actually spent a summer here at Berkeley with Martin Hedgorden, and there I learned a lot about, the kind of the model Hamiltonian approach to kind of doing certain types of chemistry. And in particular, in physics, we love to talk about spin models and lattice Hamiltonians as effective descriptions for materials. It turns out even in something like chemistry, which is a little bit, has more richer variety of structures, you can oftentimes write down model Hamiltonians that capture particular molecules that have particular features. So for example, let's say you have a molecule that has 4 metals, and the valence electrons of these 4 metals are localized. Because they're localized, instead of describing them by a fermionic degree of freedom, you can actually describe them by an effective spin degree of freedom. And then you can go ahead and try and encode the spin degree of freedom on the quantum simulator. And what's nice about this problem, in general, is that determining the coefficients of these interactions is something that's in principle, local problem and should be classically easy. But then solving, the strongly correlated spin part of the problem is something that we know is kind of difficult to do in a scalable way. So, and the nice thing is that these potentially have much nicer mappings to quantum hardware compared to, say, direct encoding of the ab initio Hamiltonian, which is why we're especially excited about them kind of in the near term. So, what would a simulation of a complex model spin Hamiltonian look like in this architecture? Well, first, even if the metal site has something like 3 valence electrons and is actually well described by a spin 3/2, we still want to use qubits to do the simulation. So we're actually going to go back to a spin 1/2 representation. And then we can kind of create clusters of qubits and use these clusters to encode kind of different spin degrees of freedom. And ultimately, we want the entire computation to live in the symmetric subspace of each of these clusters. Now, in order to engineer interactions, actually, one trick we can use is to take constituent spin 1/2s from each of the cluster, move them around, and then apply global pulses in order to generate, a particular interaction pattern. And here, we generate the interaction pattern at the level of spin 1/2 degrees of freedom, which can allow us to generate, long-range connectivity potentially, but it actually doesn't preserve the spin encoding. In principle, because these are actually happening at the level of the spin 1/2s. So then what we can imagine doing is doing another reconfiguration step and then applying a second interaction. Now this one would apply an interaction that acts within a cluster. And the purpose of the second interaction is to actually reintroduce the encoding to create the large gap between the symmetric subspace and the remainder of the subspace. And we're going to develop a Hamiltonian engineering approach that relies on alternating between these two different configurations in order to do kind of Hamiltonian and Floquet engineering. Okay, so any questions about this? Cool. So one of the big challenges actually with doing this Hamiltonian engineering is that there's actually a large separation of scales. In particular, these on-site spin degrees of freedom have an energy scale that is essentially set by local exchange interactions, whereas the interspin intercluster interactions are kind of set by super exchange. So in most systems, there's actually an order of magnitude gap in the energy between the spin projection component and the spin interaction component. And as a result, if we were to use something like a standard characterization approach or any other standard Hamiltonian simulation approach, the small parameter that determines essentially our effective step size would actually have to be small relative to the large energy scale of the problem. Now, all of the dynamics that we actually care about are in the spin symmetric manifold. And so those dynamics are really determined by the time scale associated with the smaller interaction. So one of the tricks that we came up with is essentially a Floquet engineering technique that allows you to kind of use the ability to classically solve the on-site interaction, because it's just an on-site spin term that we can efficiently simulate classically, use this classical knowledge to actually go into an interaction picture with respect to this interaction, and then essentially do Hamiltonian engineering on the interaction terms directly, but now in kind of a time-dependent picture. And what the result is that now you can do a Floquet engineering with a time scale that depends on the small interaction times the step size instead of the big interaction times the step size, giving you potentially an order of magnitude improvement in terms of how big of a step you can make before errors start to become relevant. And mathematically, the way you do this is exactly as I said. You take the alternating picture, go into an interaction picture, and now you actually have kind of build up your simulation from these rotated versions of the spin 1/2 interactions. So these rotated versions of the spin 1/2 interactions, this is the part that you kind of do on your classical computer and use these as a building block for something like a higher order Trotter decomposition, for example. Okay, so any question on this?
Yeah. I understand this Floquet engineering. This is some sort of like a BCH and then you put Floquet on that.
So if we were just using like regular Trotter, we would do BCH directly on like this part of the this part of the exponential. And then we would kind of be limited by, the norm of this term times the norm of this term. But instead we go into this interaction picture first and then do BCH. And that way we're only limited by the norm of the interaction term itself. So essentially we're using the fact that we have this efficient classical interaction picture for the on-site interactions.
So it's more like you go to interaction picture and do magnets.
Sure. Yeah. I mean, it's still discrete. So then that's why I would say it's a little bit more like BCH. It's still discrete, so you still do it like K steps associated with the period of this rotating frame. And
it's Floquet because
it's Floquet because this guy has an integer spectrum. Yeah. Yeah, so the period actually depends on the details of this interaction a little bit as well. Yeah, good question. Any other questions? Cool. So, this is also an open quantum systems workshop. So I also wanted to kind of think a little bit, actually kind of share a little bit also what we've been thinking in terms of open quantum systems. So in particular, this tool set of, digital sequences of interactions also can allow us to, imagine kind of simple engineering of Lindbladians once we introduce something like mid-circuit reset. And, kind of two problems that we've identified in this setting are things like, simulating relaxation for electron dynamics, and also, for example, simulating things like NMR spectra. These are also problems that have already kind of been proposed and studied in the quantum simulation literature as interesting near-term targets. And actually, kind of one question I wanted to pose to the group is, in these relaxation experiments, the signal that we care about is actually also kind of transient and short-lived. And so kind of one thing that we've been wondering is there a way of making Lindblad simulation algorithms that are kind of intrinsically more noise resilient, for these types of relaxation problems? Or is there some way of kind of doing this in sync with the native noise model of the system, to really try and get the most out of the near-term devices that we have? Yeah. And then, like in terms of this big set of problems and how expensive they are, where does Lindblad dynamics really come in? Is it something that lives on the bottom left somewhere? Is it like a really good target for near term, or is it something that potentially would take us many years to start to access? Potentially, yeah. But maybe it could even be something like second order suppression instead of like arbitrary order suppression. Yeah. Exactly, yeah. So like self-correcting or like dynamically decoupled or robust in some way.
Just intuitively, so if the circuit already has noise,
yeah.
Are you suggesting that when we simulate Lindblad dynamics, we put in less noise?
Yes, exactly.
Exactly. Okay, I see. But I think sometimes there is ordering in terms of the CPT maps.
Mm-hmm.
So the CPT map that you're simulating has to dominate the circuit.
Yeah. I definitely agree. And I guess like, I think an interesting regime there that I would think about is something like really small circuit level noise, say like 10 to the -4, 10 to the -5, and then understand, are there interesting Lindbladians that I can simulate really accurately in that regime? Okay. So I think, there's definitely lots of interesting questions in terms of open system dynamics. One thing we're also kind of actively exploring in the experiments is some early investigations into the Kitaev honeycomb model. So this is kind of a paradigmatic example in condensed matter physics. And, historically, it's been very difficult to do with analog simulators because the interactions are highly anisotropic. It also has a very rich phase diagram. And, one of the kind of key tools that we're planning to use in this experiment is the fact that, we can actually prepare an abelian topologically ordered state very efficiently using mid-circuit measurements and feed-forward. And in particular, we can do it by measuring the plaquettes of the Kitaev honeycomb model, and then essentially applying corrections to ensure that all the plaquettes are equal to +1. So, physically, each of these plaquettes kind of maps to a set of 6 atoms on this array on the right. And then when we do the correction process, when we do the measurement process, we would introduce an array of stabilizer qubits and then kind of go step by step and then measure each of the terms in this stabilizer. And then we would move the stabilizers away, image the system, and then based on the image, do a round of decoding to determine, where are some Pauli flips we can apply to the system in order to flip all of the -1 stabilizers back to +1. Because when we do this process, these stabilizers are kind of randomly chosen +1, -1.
So this is exactly solvable, is it?
Yes, exactly.
The purpose of the experiment.
So the purpose of the experiment will be twofold. First will just be to kind of see if we can use the exactly solvable physics to prepare a non-abelian spin liquid state here. So even though it's non-interacting, it is still a non-abelian topologically ordered state, which is interesting. And then actually, if that all goes well, and this is all very preliminary still, But if that goes well, ultimately our hope is to turn interactions on and actually kind of see what interactions look like in this phase too. Yeah, because in terms of the control, the interactions are also pretty easy to do. I think that's actually one of the features that makes it good, because we can use our classical simulations to kind of really benchmark and calibrate and get the experiment working. Yeah. Lindbladian would happen during the next experiment if we come up with a good idea. Yeah. That's right, exactly. And kind of we're kind of using this measurement feed forward based state prep, which is a kind of like Ancilla based algorithm. I'd have to ask an experimentalist for a specific number, but I think the imaging time is on the order of also about 100 microseconds. Yeah, so it's all still, huh? So the important number to compare it to is the coherence time of the qubit. And compared to the coherence time of the qubit, it's still quite short. Yeah, so we're gonna, yeah, so the decoding here is all done kind of very quickly. Yeah. And I mean, even then, like we only have to do one round of decoding, so it's actually not too bad. So here this is not an error correction experiment. This is purely using measurement-based state preparation as a way of preparing a topologically ordered state.
You're not going to check that your extraction procedure doesn't introduce more error.
Yeah, so we are characterizing this process. Yeah. And actually, so I don't have a slide on this, but we are using simple forms of error detection actually to kind of get more out of this. So it's not fault tolerant, but you can actually use the stabilizer structure plus error detection to kind of do a little bit of the check of the state preparation as you're suggesting. Yeah.
Yeah, so your mid-circuit measurements will be noisy. How do you certify that your final state is still topologically ordered? Because why wouldn't that be destroyed by the noise?
So actually, in general, it will be destroyed by the noise. Like it won't be preparing a long-range topologically ordered state. Yeah. But the hope is that the density of these vortex excitations is low enough that we can still see the interesting physics.
Yeah, do you have anything concrete to see? Any observables that you can measure to sort of give evidence that the state is interesting?
Yeah, so we have ideas for observables to measure in the non-abelian phase that would help us characterize the nature of that non-abelian phase. Yeah. I think actually is there a question? In the interest of time, I think I'll kind of keep going. Okay, yeah. So then in the end, we do this kind of correction step. So yeah, and actually, so like the next thing, once you do state preparation based on measurement and feed forward, then you would actually want to run another state preparation circuit on top of that in order to actually go from the topologically ordered abelian phase to the topologically ordered non-abelian phase. And that's really ultimately our target, is this topologically ordered non-abelian phase. And because of the exact solvability of the system, we actually have very efficient circuits as well that we've classically optimized that can get us into this regime. And also just kind of as something to mention, at the end of the day, one thing we're very excited about is probing dynamics and excited state properties of phases of matter. And so, in parallel, we've also kind of been developing a set of tools for kind of using time evolution and snapshot measurements to really extract properties of ground states, but also excited states through this kind of through the dynamics. Yeah. So this is also something I'd be happy to talk about if anyone's interested. Okay, so yeah, so that's kind of what I was planning to talk about in terms of the digital quantum simulations of physical qubits. And ultimately down the road, if we really want to make progress, then we're going to have to start doing things with error correcting codes. Because this is really the only realistic route we have for getting error rates on the order of, say, 10 to the minus 10. And a lot of these controls that I was describing are actually also really naturally suited to particular forms of quantum error correction. So in particular, this parallel control in global laser pulses can really be used to kind of control logical qubits at a time instead of physical qubits at a time. So imagine, for example, we have 9 small surface codes. Then we can use kind of local single qubit rotations to apply transversal gates to single surface codes. And then we can also kind of use reconfiguration and global Rydberg pulses to apply entangling gates between different surface codes. And so, this actually forms kind of a fundamental gate set for quantum error correction. And, it's all using here transversal operations. And, these transversal operations are nice for a few reasons. One of them is that they're intrinsically fault tolerant. So errors actually propagate in a much more friendly way when you're using transversal operations. And the second one is that these are actually also very efficient to control. So we only kind of have to do one move and one gate in order to realize entangling logical qubit operation. Now, from the point of view of the talk today, I'm going to kind of emphasize a particular aspect where we studied some really simple 3D codes. So 3D codes are super interesting because they actually have very efficient transversal non-Clifford gates. And as a result, they can also be hard to simulate. And so we kind of were asking, can we do interesting, simple computations with, logical circuits? And one of the targets that we identified was actually using this small 832 code. So this is a code that uses 8 physical qubits, 3 logical qubits, and has distance 2. So it's an error detecting code. And here for reference are the logical operators of the code. They correspond to faces for the x's and edges for the z's. And these codes are really nice because they also come equipped with a pretty intricate gate set. So for example, you can use single qubit rotations to implement a logical CCZ between the 3 qubits in the block. You can also use local addressing to implement local CZs. And then you can also use kind of permutation and physical rotations to do in-block CNOTs and importantly, transversal CNOTs between 2 of the different codes. So, in this work down here, we kind of used 16 of these code blocks to run some very complex circuits on 48 small logical qubits, really generating non-Clifford entanglement and kind of at a large scale with distance 2 codes. So, yeah. This task of doing complex quantum circuits, and we're specifically targeting a sampling task, looks as follows. So kind of as usual, when you're working with error correcting codes, you take your initial states, you prepare them, and then you run the circuit. And now you're kind of programming the circuit at the logical level instead of the physical level, if you're like a circuit designer. But then when you measure the qubits, you kind of get this additional information here, which is the information not just about the logical degrees of freedom, but also the stabilizers. And in particular, these stabilizers provide you a little bit of information about what types of errors occurred during the computation. And you can use this this knowledge about the errors that occurred to actually now go ahead and improve, your logical fidelity by throwing away the samples that likely are corrupted. And, that's what kind of error detection and post-selection allows you to do. So we kind of use like a more refined version of this, where we did partial post-selection based on the number of stabilizers that were violated. And here is kind of some data for the 12 qubit version of this experiment. And kind of here in the front, this is kind of the raw bit string distribution without any error detection. And what you see as you move farther down with increasing amounts of error detection is that the bit string distribution starts to approach the true theoretical distribution, which is probably really hard to see. But it starts to approach the true theoretical distribution quite quickly. Yeah. You can also kind of quantify this into a single number using the cross entropy, which is kind of a proxy for fidelity for these IQP circuits. And you kind of see that the cross entropy grows very quickly as you increase the number of amounts of post-selection that you do. Yeah. That's a great question. Here we just throw the whole string. Yeah. We don't do any, that's a great question though. Yeah.
Could you speak more about how exactly error detection is being done in this study?
Yeah, so I guess the key actually is the stabilizer. So like when you measure the qubit, you kind of naturally get the stabilizer information out. You can also compute that from the physical measurement outcomes. And it turns out that these stabilizers allow you to essentially detect whether or not a single error occurred. So if you're promised that only one error occurs in this part of the circuit, then you're guaranteed that it's going to be detected by a stabilizer. So that's kind of how you can use it to do error detection. If this value is -1, then you're likely to have had an error.
Can you say again, what's the benefit of a single logical qubit code?
Oh, yeah. So like it actually turns out that I guess with these codes, like these are kind of the gates you can think about. So like when we do these entangling gates between the logical qubits, these entangling gates are kind of happening actually by addressing a single logical block at a time. So you kind of think about 8 of these physical codes as representing one block, and you control this block to realize your like some of the simple gates in the circuit.
The benefit of this is
It's very easy experimentally. That's the primary benefit. So it's like very high fidelity and very easy experimentally. I shouldn't say very easy. I think these things are still pretty challenging, but it's like doable experimentally.
but not 2D code. And 2D, there are no-go things saying there isn't any transversal.
That's right. Yeah. So with 2D codes, you could get some of these like CZ and C0 operations, but you wouldn't have any non-Cliffords. Yeah. So those circuits at the end would all be easy to classically simulate. And so like, for example, actually, if you look at like the bit string distribution, there's like a lot of features here and like many different probabilities that you measure. If you're working with a Clifford circuit, that doesn't happen. With a Clifford circuit, they're kind of binned into discrete units.
And these 832 codes are just some optimized code, or they belong to a certain class?
It's the smallest 3D color code. It's the smallest 3D color code. So there's like, it kind of belongs to an asymptotic family. Yeah. And actually, it's a good time to, actually, Dominique, who just joined here, was kind of one of the leads on a theory paper that we put out. He's in the back. And so, there we actually talk about kind of the scaling of this approach in much more detail. Yeah.
What was the rate of post-selection error in the, how many strings do you throw out as you grew the logical circuit?
Yeah, so this one here is like, the acceptance fraction is around like 17%.
That as the logical circuit grew in number of gates.
Oh, I'd have to look at the paper for that, yeah. We didn't grow the circuit depth too much. We mostly just grew the size, and then we're working with kind of these log depth circuits that have a hypercube structure. Okay, so one of the questions that we started asking recently is, we see that error detection works very well at suppressing the error rate. However, we can also ask kind of a more refined question, which is, how does error detection change the form of the logical errors? So kind of motivated by that question, we recently started looking into the form of logical errors with Daniel Mark at MIT and also Robert Huang, who's here. And yeah, so one of the things that we realized very quickly is that actually logical level errors are potentially kind of complicated. So they really emerge from the physical errors through this kind of process, where the physical errors occur and then you do some amount of decoding and error detection, and that gives you some logical noise model. And so for example, here, because we're working with these encoded qubits, actually you see that IID physical errors can very naturally produce something like a correlated error at the logical level, just because you have these 3 kind of overlapping logical qubits. Kind of a sign that logical errors already start to behave non-trivially. However, if we just kind of look at this bit string distribution that I showed on the last slide, and we use some like standard white noise type fit, we actually see that it's pretty hard to distinguish the experimental data from the white noise fit, because the actual data set only has so many samples. However, what we can do is we can use some more advanced noise learning techniques to try and systematically extract the properties of the underlying logical errors. And indeed, kind of a key feature is that logical errors that occur, physical errors that occur in different parts of the circuit, and also logical errors that occur in different parts of the circuit, propagate differently. And because they propagate differently, they'll have different consequences on the output bit string distribution. And we can use that to distinguish between errors that occur in different parts of the circuit. So for example, here, I'll show you errors that occur here versus errors that occur here. So these kind of occur at the beginning of the circuit, and this occurs somewhere in the middle. And when we apply our technique, we essentially find like a distribution of single block logical errors located here. The blue line corresponds to the error distribution before correction, and the orange line corresponds to the error distribution after correction. If we now move to the other part of the circuit, which is kind of in the middle of the circuit. Now we see this is what it looks like before correction. This is what it looks like after correction. If you just take the blue line and rescale it by 4p squared, you actually see that it does a very good job explaining the decrease from pre-error detection to post-error detection based on, yeah, just kind of the quality of this fit. But really interestingly, if we do the same procedure on the other side, we actually find that this 4p squared doesn't do a very good job of fitting this data. So, okay, what's going on there? Why didn't error detection work? Well, it's actually because in the experiment, we use non-fault tolerant state prep. So the state prep circuit isn't protected to distance 2. And so there's single errors that can occur in the state prep circuit that actually lead to uncorrectable logical errors, at order p. And you can actually see that reflected in the data using these techniques. A second kind of question that we asked, motivated by some, yeah.
But they were after state preparation.
Yeah, so this is like single qubit rotations at the physical level. So it turns out that these are the z errors. So they kind of pass through there. Yeah, that's a good question. I should probably draw it on the other side. Yeah. These are state prep errors. Good. Yeah, so we also looked into non-poly errors, kind of motivated by some kind of pioneering theory work, because one of the key features of error correcting codes is that continuous errors at the physical level actually turn into a discrete set of errors at the logical level. And this discretization is really key to the ability to do control and efficient feedback in order to kind of steer your computation in the right direction. However, interestingly, when we kind of applied the procedure to try and fit the rates of non-poly errors in the system, we found actually that there aren't too many non-poly errors, but the ones that are there are actually amplified by the error detection procedure as opposed to suppressed by the error detection procedure. So we were also kind of trying to understand what was going on there. And actually, we think we have a mechanism essentially arising from treating the QEC code itself as a kind of open quantum system. So, we can think about the logical code space as being spanned by these 8 different basis states. And kind of looking microscopically at the structure of the states, we see that the all 0 state is a superposition of all zeros plus all ones. And we actually see the other 7 states are a superposition of 4 zeros and 4 ones. So this is a little technical, but the reason why I'm emphasizing this distinction is because if now we hit the system with some global over-rotation, like a coherent error, what we actually find are, 7 of these 8 logical states live in a decoherence-free subspace. Both of these 2 contributions are affected equally by this global Z over-rotation. In contrast, the all 0 state is special, and it's the only one that picks up a relative phase in the superposition, just due to the structure of the code itself. And as a result, if we now go ahead and measure, say, the X stabilizer at the end of the computation, we see that this coherent over-rotation actually ends up acting kind of like a loss or erasure channel at the level of the logical qubit, because only the all 0 state maps to this violated stabilizer. The other 7 states don't. And so, kind of the conclusion here is that if we kind of think about this process of the error occurring plus the error detection, then it really ends up looking like an amplitude damping channel at the logical level. Yeah, so I think one of the big takeaways here is that kind of this process of how logical noise emerges in the system is actually quite subtle. And in particular, these tools we've been developing that help us kind of do detailed characterization of the logical noise model might actually be quite an important part of doing useful quantum simulations with near-term error-corrected devices. Because, being able to characterize the form of the logical noise will actually be very useful for developing things like error mitigation and algorithm design, kind of in the early fault-tolerant regime. So, with that, maybe I'll wrap up. So to kind of summarize, I think really the high-level vision here is let's think about the algorithms, architectures, and applications all together in order to really identify good applications and then come up with optimizations to implement them in our hardware. And we're kind of very excited in particular about this era of early fault tolerance and what could we really do with these? Can we start to answer some interesting scientific questions? And yeah, so then I'll also kind of thank my collaborators on these projects. This has really been a big team effort, a lot of this stuff. So here's the first page on most of the theory stuff. And then this is kind of our experimental and experimental related theory team. And thank you all for your time. Yeah. Also, I prepared a discussion slide if anyone's interested. So, kind of related to the stuff that we were just talking about.
Well, this is logical noise learning. Does the noise also depends on the circuit? Like the algorithm you use for that?
Yes, it does. Yeah.
Okay, so then each time you run the algorithm, you have to characterize.
If you were gonna, yeah. So I mean, it's more likely that as we start to do this, we would start to kind of figure out what the general features are. So we can probably start to do some of that without having to rerun the procedure. But in general, yes, we would have to rerun it. Yeah. So for example, like the structure, these non-Clifford gates actually change things quite a bit. Yeah. Good question.
So during co-design, what
Yeah.
are some parameters to optimize for? I mean, there's the total number of T gates.
Yeah. Yeah, so I guess at the end of the day, I would say that the most important parameter to optimize is like the quality of the computation you're trying to do, however you define quality. So it's very soft. Now, like I would say that in practice, once you fix your application, you know, say you're trying to compute the spectrum of some like molecule, then using that fixed application, you can determine what the actual cost is that you're trying to minimize. So it'd be like the errors that are destructive to your signal. And then you would determine kind of like what are the hardware limitations to actually minimizing that output in your signal. So it ends up being kind of a more nuanced approach than like optimizing one number. So it's kind of a cop-out answer because it didn't give you a specific number, but that's I think kind of the way the approach works.
So if you figure out that you have some particular like non-Pauli noise in your circuit, what do you do then? Like you feed it into your decoder and you get better.
That's a good question. We haven't thought too much about decoding here because in some sense we're always working with like an optimal decoder. I would say I would characterize that as like an error mitigation strategy. You could use it for improving your error mitigation. Yeah, because you can use the knowledge of the noise to kind of fix it. But how to do that scalably is, I think, really it's an open question. Because here we do exact simulation. So
50 to 100 logical qubits is still within the range that you can apply this like non-scalable error mitigation strategies.
Potentially, yeah. So I mean, like we probably wouldn't want to do like distance to error detection because the acceptance fractions are pretty small here, you know. But if we can still kind of do some amount of post-selection error detection to reduce like the most harmful error events in that condition. And there's been some recent papers kind of analyzing how much this can improve things, the like partial error detection approach. Yeah. I think 50 to 100 logical qubits is roughly the range for trying to implement things on like a couple thousand physical qubits.
And the post-selection doesn't introduce much bias, or there's a way to bias?
I mean, in principle, if you can wait long enough, you can use more post-selection, right? So like post-selection is nice in the sense that it really improves your logical error rates, but the cost is it's exponentially expensive. Yeah. So I think it's like a trade-off, right? How much post-selection you want to use would depend on the
Well, maybe
how the hardware ends up working.
Maybe I was just asking a naive question.
Yeah.
You
Either way.
Yeah, and that also introduces a bias.
Like in terms of the algorithm performance.
Yeah, in terms of the algorithm.
That's a good. I guess in some sense that's like what this funny logical noise observation is. You know? Yeah, that sometimes post-selection can introduce some type of bias. But you can also think about that as an effective logical error. You know, under the channel induced by the post-selection. And I think that's an equivalent way of thinking about it. Yeah, that's a great question. Yeah. We also think that as we increase the code distance, the effect of these errors should kind of decrease. Yeah, and you know that pretty well. So these are probably more in like the near term, small distance limit. Yeah, good question.
Yeah, let's thank the speaker.